The next one is going to be the product rule. The product rule says if f of x and g of x are differentiable, then the derivative of f of x times g of x is found by taking f of x times the derivative of g of x plus the derivative of f of x times g of x. Another way to change that notation to make it a little bit more straightforward is that if you have f of x times g of x prime, the way you find its derivative is by taking f, your first one, times the derivative of the second one, plus the derivative of the first one times the second. Both of these say the same thing, just using some slightly different notation. I wish I could tell you that taking the derivative of the product of two functions was as straightforward as taking their limit. If this were a limit instead of a derivative, you'd just take the limit of the first one times the limit of the second one. But in derivatives, that's absolutely not true. If you want the derivative of the product of two functions, you need the first one times the derivative of the second one, plus the derivative of the first one times the second one. There's a sum in your product rule. Now, that's the bad news. The good news is, in some ways, the order of this doesn't matter. Because of the fact that this contains addition, well, remember, addition is commutative. I could just as easily write this as f prime g plus f g prime. It means the same thing. Also, these are each individually products, and multiplication can go in any order. It's commutative as well. But when you're looking to take the derivative of the product of two functions, what this will boil down to is you will have two terms being added together. In the first term, you need one of the functions times the derivative of the other one. And in the second term, you need to change which original function appears and put in the derivative of the other. Order is a little interchangeable here. Let's take a look at some examples. Use the product rule to find the derivative of h of x equals the product of 3x minus 2x squared times 5 plus 4x. So this specifically asks us to use the product rule to find the derivative, so that's what we're going to do. So this derivative will either be h prime at x or dh dx, depending on which notation you're using. Since we're using the product rule, my first function will be 3x minus 2x squared, and my second function will be 5 plus 4x. So this derivative is given by my first function, 3x minus 2x squared, times the derivative of my second function, 5 plus 4x, prime, meaning I haven't taken its derivative yet, I will, plus the derivative of my first function, so 3x minus 2x squared prime, times the second function, 5 plus 4x. So when we actually take those derivatives, what we'll get is 3x minus 2x squared. What's the derivative of 5? It's 0. What's the derivative of 4x? It's 4. Plus, we then need the derivative of 3x minus 2x squared. The derivative of 3x is 3. The derivative of 2x squared is 4x, so minus 4x, times the second function, 5 plus 4x. Now, for the sake of the problem that I have coming next, I'm going to go ahead and distribute and combine like terms for these. So we're going to get 12x minus 8x squared plus, the next one's a FOIL, so that's 15 plus 12x minus 20x minus 16x squared. So that when you combine like terms, you will get negative 24x squared. See, we'll have 24 minus 20, so plus 4x, oops, I forgot my squared, plus 15. And that's the derivative found by using the product rule. Now what we want to do in the next example is take the same function. This is still h of x equals 3x minus 2x squared times 5 plus 4x. We're going to multiply this first. This is a function that can be first simplified by distributing or foiling. So we're going to actually do that first and then use the differentiation formulas that we learned before the product rule to find the derivative and compare the results. So if I simplify first, so this is h of x, this is not yet the derivative. If I FOIL, I get 15x plus 12x squared minus 10x squared minus 8x cubed, which if you want to go ahead and simplify that even further, you can write that as negative x cubed. Combine these for plus 2x squared and then plus 15x. So now we can take the derivative of h by using just the sum and difference rules and the power rule and the constant multiple rules. So the derivative of negative 8x cubed is negative 24x squared. The derivative of 2x squared is 4x, and the derivative of 15x is 15. Compare that to the previous answer. Sure enough, they're the same. In both cases, we get negative 24x squared plus 4x plus 15. So the reason I went ahead and put this example in is because I wanted to make sure I pointed out that while the product rule is not as simple as we would like it to be, it is correct. If you tried to do this the wrong way, generally when students want to do this the wrong way, what they want to do is just take the derivative of the 3x minus 2x squared and multiply that times the derivative of 5 plus 4x. Watch what happens when you do that. Your derivative will then be, the derivative of 3x is 3. The derivative of negative 2x squared is going to be minus 4x. And then your second one, the derivative of 5 will be 0, and the derivative of 4x is 4. So notice when you distribute that, you're going to get 12 minus 16x, which is definitely not what you got there. So just taking the derivative of the first function times the derivative of the second function is usually not going to get you the correct answers. Let's take a look at another example of using the product rule. If h of u equals u times g of u, and g of 3 equals 5, and the derivative of g at 3 equals 2, find the derivative of h at 3. Okay, that looks like a lot of gibberish at first. We're looking for the derivative of h at 3. We're given the function h of u. So can we find the derivative of h? Look at how h is defined. It's u times g of u. That makes it a product. So when we go to find the derivative of h, that will be the derivative of h at a general u. I'll worry about the 3 in a minute. The derivative of h at u, we're going to have to use product rule. We need u times the derivative of g of u. Well, I don't know what g of u is. I didn't define that for you. So the best I have for you is that the derivative of g of u is g prime of u. Plus, what's the derivative of u with respect to u? It's 1 times g of u. So in other words, this is u g prime of u plus g of u. That's the derivative of h with respect to u. So now if that's the derivative of h with respect to u, what do we get for the derivative of h specifically at 3? That says the same thing it's always said. Plug in 3 everywhere you see u. So instead of u, I write 3. In the derivative of g, instead of writing g prime at u, I write g prime at 3. And then plus g of 3. Now I get to use the given information. G of 3 is 5, and the derivative of g at 3 is 2. So this is 3 times 2 plus 5. This is now just a very simple arithmetic problem. Turns out the derivative of h at 3 is 11. So that's a more general look at how we can apply the product rule. Okay, so here's another example. We're going to differentiate the function f of t equals the square root of t times a plus bt. And again, I've purposely given you one that has a lot of letters on the right-hand side. Your first goal is to identify which of those is a variable. Well, because I've told you it's f of t, that automatically tells you t is the variable in this problem. So what does that make a and b? Those are constants. So we want to take the derivative of this, and we notice that this is a square root of t times a plus bt. So there's a multiplication going on here. And since we've been talking about product rule, let's go ahead and get some practice using that. So I'm going to do this using product rule. So the derivative of f at t, or df dt, is found by the first function. Now keep in mind that the square root of t is the same thing as t to the 1/2. So that's the first function, t to the 1/2, times the derivative of a plus bt. So what's the derivative of a with respect to t? A is considered a constant, so its derivative will be 0. I'll go ahead and write it in. You don't have to, but just so it's obvious where I'm getting my numbers. Then what's the derivative of bt? The derivative of bt with respect to t is b. If you're not sure about that, that one has a tendency to be a little less obvious. Think of it this way. What's the derivative of 5 times t? It'd be 5. What's the derivative of negative 6 times t? It'd be negative 6. So what is the derivative of b times t? It will be b. Okay, so that's how you get that derivative. Plus, I need the derivative of t to the 1/2, so that's 1/2 t to the negative 1/2 times the second function, a plus b t. So if we clean that up just a little bit, that tells me that my derivative, the derivative of f at t, is b times the square root of t plus the t to the negative 1/2 will move down to the denominator along with the 2. So you'll have 2 and then t to the 1/2, but that's the same thing as the square root of t, with a plus bt in the numerator, and that's the derivative. Okay, let's take a look at this example. If f of x equals x times e to the x, find f prime of x and f double prime of x. In other words, the first and the second derivative. So we notice that f of x contains the product of x and e to the x. So that indicates that we're going to need to use the product rule to take this derivative. So when we look at f prime of x, we take x as is, so the first function as is, there's x, times the derivative of e to the x. But the derivative of e to the x is e to the x, plus the derivative of x with respect to x, which is 1, times the second function as is, which is e to the x. Clean it up just a little bit, and what we're going to get is x e to the x plus e to the x. And that's an acceptable way to leave this, but what we can also notice is that there's an e to the x in both of these terms that can be factored out. So we can take that out and call this e to the x times x plus 1. And like I said, either one's acceptable, but the reason I might be interested in doing this is, notice I'm going to have to find the second derivative. And if I write it in this form, then when I want to take the derivative, it's just another product rule. Whereas if I leave it in this form, then not only do I have a product rule sitting here for x times e to the x, I'll also have an additional term to take the derivative of. So, but either one's fine. You should get the answer either way. So the second derivative with respect to x, I'm going to use our factored out form. I'll leave e to the x as is, and then I need times the derivative of x plus 1. Well, the derivative of x is 1, and the derivative of 1 is 0, so that's just going to be times 1, plus the derivative of e to the x, which is e to the x, and then leave the second function as is, so that's x plus 1. So again, I can clean this up a little bit. If you notice, there's an e to the x in both terms, so I can factor it out. We can do this in one step or two steps. When I take e to the x out of the first term, I'm left with 1. When I take it out of the second term, I'm left with x plus 1. But notice I now have like terms with the plus 1 and plus 1. So I get e to the x times x plus 2. And that's my first and second derivative. Now that we've discussed multiplication, the product rule, let's talk about the quotient rule, division. So it starts off the same way. If f of x and g of x are differentiable, then if you want to take the derivative of the ratio or the quotient of those two functions, the way you take the derivative of a quotient is you take the denominator as is, g of x, times the derivative of the numerator, so d dx f of x, minus the numerator as is, times the derivative of the denominator, d dx g of x. And then you take all of that and you divide it by g of x squared. That's the denominator squared. Okay, so, or in the slightly simplified notation, if you want f over g prime, that's g f prime minus f g prime all over g squared. Believe it or not, there's another way you can remember this. Most students, if you ask them a year or so after they learn this, what's the quotient rule, most of them will start talking to you about highs and lows. What we do is we say, okay, call f your high function because it's on top, and call g your low function because it's on the bottom. So it's literally their position in the quotient. So then your derivative, your quotient rule becomes low d high minus high d low all over low low. Low d high minus high d low all over low low. Generally, walk into any math tutoring center and ask them for the quotient rule, and the math tutor will probably start talking to you about highs and lows. So that's just another way to remember it. Let's take a look at an example. Find the derivative of f of x equals 5x minus 2 over x cubed plus 4. So this 5x minus 2 is going to be my high function, my numerator, and x cubed plus 4 is going to be my low function, my denominator. So when I find the derivative of this, so f prime of x or df dx, either one, I need the denominator as is, so x cubed plus 4 times the derivative of the numerator. So the derivative of 5x is 5, and the derivative of negative 2 is 0. So that's just 5. Minus the numerator, 5x minus 2, times the derivative of the denominator. So the derivative of x cubed is 3x squared, and the derivative of 4 is 0. All over the denominator squared, x cubed plus 4 squared. Now there is often some kind of simplification that can be done. For this particular example, I'm going to go ahead and skip any simplification just because I want us to be able to concentrate on the actual quotient rule. So notice quotient rule in comparison to product rule is much more stringent about what gets placed where. Let me back up to the previous slide. Because the quotient rule contains subtraction instead of addition, you must go in the correct order in the numerator, or you're going to be off by a sign. You must have, for your first term in the numerator, the denominator times the derivative of the numerator. And for your second term, you must have the numerator times the derivative of the denominator. So order is actually much more important in the quotient rule than it is in the product rule. Now you can still technically switch the multiplication. The multiplication is commutative, but subtraction is not. Let's take a look at a couple more examples where we'd like to maybe decide if we'd like to apply the quotient rule or not. So for example, find the derivative of 1 over x. I definitely see a quotient here, and quotient rule will work. So if I use the quotient rule, I'll have d dx of 1 over x equals, so we'll have the denominator times the derivative of the numerator. Well, what's the derivative of 1? It's a constant, so its derivative is 0. Minus the numerator times the derivative of the denominator. Well, what's the derivative of x? It's 1. All over the denominator squared. So x times 0 is 0. In my numerator, I get a negative 1. And in my denominator, I get an x squared. So that is the derivative of 1 over x. There is, however, a slightly faster way to do this. We have actually already made use of this technique in some of the previous examples. You can rewrite 1 over x using negative exponents. Instead of dealing with it as 1 over x, deal with it as x to what power? That'll be negative 1. Now you can just apply the power rule instead. Drop the negative 1 down. You then have x raised to the new power of negative 1 minus 1, also known as negative 2. Well, that's the same thing as negative 1 over x squared. So notice whether you use quotient or whether you first rewrite and use power rule, you get the same result. When you run across a problem where you get a choice, the power rule is probably a little bit faster. Let's take a look at another one. We want to find d dx, the derivative with respect to x, of 5 over the cube root of x squared. Again, when we're taking derivatives that have radicals in them, we need to rewrite using a to the m divided by n equals the nth root of a to the m, which is the same thing as the nth root of a raised to the m. Okay, this is the rule we need to use. So when we go to rewrite this, we get d dx of 5 over, 3 is your index, and 2 is the exponent. So this is the same thing as x raised to the what? That should be 2/3. So now we're looking at an example very similar to the one we just did. So you can use quotient rule on this. It's not incorrect to do so, but it's probably just a little bit faster to rewrite this as 5 times x to the negative 2/3 instead. Notice I'm leaving the d dx here because I have not taken the derivative of this yet. Now that I have it rewritten to where I can apply power rule and the constant multiple rule, I'm going to go ahead and take the derivative. So I will drop the d dx. I will take 5 times the negative 2/3 for negative 10/3 times x raised to the new power of negative 2/3 minus 1, which is negative 5/3. You can then also put this back into a form much more similar to its original form by taking the negative 10 and putting the 3 in the denominator. In order to take the negative 5/3 in the exponent and change it to a positive exponent, you would put it in the denominator and then change from a rational exponent to a radical. So that'd be 3 times the cube root of x to the 5th power. You don't necessarily have to rewrite from here to here, but you're going to see it often in your book, in your solutions manual. When we start plugging numbers into these derivatives, we're going to need to know what it means to raise a number to the negative 5/3, for example. And all it means is to take the number, put it in the denominator, and then take the cube root of the number and raise it to the 5th power. This one's asking me to find the equation of the tangent line to the curve y equals e to the x over 1 plus x squared at the point 1/1/2 e. So we're finding the equation of the tangent line, which means we need 2 pieces of information. We need slope and we need point. We've got the point. The point is 1/1/2 e. So what I need is the slope. Once I have both of those pieces of information, I can use the point slope form. Y minus y sub 1 equals m times x minus x sub 1. So we'll take the derivative, and notice that since this is a quotient, it's a ratio, we are going to need to go ahead and use quotient rule to take this derivative. So we will have the denominator, which is 1 plus x squared, times the derivative of the numerator, which is e to the x, because the derivative of e to the x is e to the x, minus the numerator, e to the x, times the derivative of the denominator, which the derivative of 1 is 0, and the derivative of x squared is 2x, all over the denominator squared. So 1 plus x squared quantity squared. I'm going to clean this up a little bit before I start dealing with the point. Notice both of these two terms have an e to the x in common, so I'm going to factor that out. When I do that, in the first term I'll be left with 1 plus x squared, and in the second term I'll be left with minus 2x. And again, that's still over the same denominator, 1 plus x squared squared. And if you notice, this is x squared minus 2x plus 1, if you think of it in a different order, which is factorable. That happens to factor to x minus 1 times x minus 1, which is x minus 1 squared. And the reason you want to kind of just keep an eye on whether or not that numerator factors or not, there are going to be occasions where maybe you can do some cancellation between the numerator and the denominator. Now that did not happen for us, but we never would have known whether or not it would cancel unless we factored. So that's why I went ahead and did it. So this is the slope of the tangent line at all points that have an x value. So given any x value, I can tell you the slope of the tangent line to this curve. But I'm specifically looking for the slope of the tangent line at the point 1/1/2 e. So I'm not really looking for y prime of x, which is what I have. What I'm looking for is y prime of 1. This will give me the slope of the tangent line specifically when the x value is 1. So when we plug 1 in, we're going to get e to the 1, which is just e. In the numerator, we're going to get 1 minus 1 squared. Yes, that's going to be 0. And down here, we're going to get 1 plus 1 squared, and 1 squared is just 1, and then squared. So because of that 1 minus 1 in the numerator, what you're going to notice is that this turns to 0 over, what would that be, 4? So it's 0. So the slope of the tangent line at this point is 0. So think about what that means for a second. If the slope of the tangent line is 0, what kind of line does this have to be? It's got to be horizontal. Okay, well if it's a horizontal line, then its equation we don't even need this entire point slope form. Horizontal lines always have the equation y equals some number. And what does y equal? It equals the y coordinate. Y equals 1/2 e is going to be the equation of the tangent line to the curve at this particular point. Let's take a look at another example. Find the equation of the tangent line to the curve y equals the square root of x over 1 plus x squared at the point 1/1/2. So notice we're right back to find the equation of the tangent line. To find the equation of any line, you only need two things. You need point and slope, at which point you can then use the point slope form. Y minus y sub 1 equals m times x minus x sub 1. We have the point. The point is 1/1/2. So all we need is the slope. Since this is the tangent line, we need the slope of the tangent line, also known as the derivative. So since we need the derivative of this function, we look, and sure enough, that is going to require a quotient rule. So we take the derivative, either y prime or dy dx, and we use quotient rule. So we get the denominator times the derivative of the numerator. Remember, the square root of x is x to the 1/2 power. So its derivative will be 1/2 times x raised to the 1/2 minus 1 for the negative 1/2. We then need the numerator, x to the 1/2, times the derivative of the denominator. The derivative of 1 is 0, and the derivative of x squared is 2x, all over the denominator squared, 1 plus x squared squared. Okay. So this derivative has quite a bit of simplification that could be done. We could do things like distribute 1/2 x to the negative 1/2 times 1 and then times x squared. That would not be incorrect. We can take x to the 1/2 times 2x. That would not be incorrect. However, we are specifically looking for the slope of a tangent line. We're looking for a number. Assuming I already did all those simplifications, how would I go about finding that number? Well, the derivative is the slope of the tangent line, so you need to plug in an x value, specifically the x value of 1 for this point. So if I'm going to end up just plugging 1 in for x, it's not wrong to do the algebraic simplification, but I'm going to go ahead and just plug 1 in for x immediately, just on the off chance that I might have an algebraic error while I'm trying to simplify. So I'm going to go ahead and just plug in 1. So I get 1 plus 1 squared, which is 1, times 1/2 times 1 raised to the negative 1/2. Well, that's just 1. Minus 1 to the 1/2 is 1 again, times 2 times 1 for 2. Aren't we glad they gave us 1? If they had given us any other number, this would be a lot uglier of a problem. In the denominator, we'll have 1 plus 1 squared, so that's 1 plus 1 squared. So when we're done, we have 2. We have 1/2 and 1 in our first term, minus 1 times 2 gets me 2, over 2 squared, which is 4. This becomes 1 minus 2, which is negative 1/4. So the slope of that tangent line should be negative 1/4. Now that we have the slope, we're pretty much there. We just need the y minus the y value, which is 1/2, equals the slope, which is negative 1/4, times x minus the x value, which is 1. So if we isolate the y, we'll get negative 1/4 x. That will be plus 1/4 plus 1/2 for plus 3/4 total. There is the equation of the tangent line to this curve at the point 1, 1/2. So keep that in mind as we take a look at the next example. This example asks us to find the equation of the normal line to the curve, y equals the square root of x over 1 plus x squared at the point 1, 1/2. So notice I've given you the same curve and the same point. But now we're looking for the equation of the normal line. So the first question you should ask is, what's a normal line? So in general, when you have a curve, and you're talking about this curve at a particular point P, if your tangent line at that point P looks like this, then the normal line at P is the line perpendicular to the tangent line at P. So if this is your tangent line, then this, pretend that goes through P, is your normal line. So these two are perpendicular to one another. They come at a right angle to one another. So if two lines are perpendicular, what's the relationship between their slopes? They're opposite reciprocals. So what we know from the previous example is that the slope of my tangent line was negative 1/4. So what does that tell me the slope of my normal line is going to be? It should be 4. Once you know that, given that you're looking to find the equation of the line, you still only need two things: a point, which we have, and now the slope, which we also have. Believe it or not, once you find the equation of a tangent line, the equation of a normal line is very quick. It's y minus the y value equals the slope, which we decided is 4, times x minus the x value. So the equation of that normal line will be y equals 4x. We'll have minus 4 plus 1/2 for negative 7/2. That's the equation of the normal line to the curve at the point 1, 1/2. So I threw this one in here because A, it's going to show up in your homework, and B, you will be discussing normal lines in your physics and engineering classes as well. Let's take a look at another example. At what points on the hyperbola xy equals 12 is the tangent line parallel to the line 3x plus y equals 0? Okay. So we're talking about a hyperbola, xy equals 12, and we're talking about a tangent line to that hyperbola, which means we're probably going to need to involve a derivative. If we need to take the derivative of x times y equals 12, that's not quite the same form we have seen this written in. Normally when we see these, they have already been solved for y or f of x, But the good news is, since this is a hyperbola, it's a very easy fix. You just rewrite it as y equals 12 over x. And you'll be able to very easily take the derivative of this. But let's see if we can get a little bit more of a big picture idea of what it is we're looking for. So I have this hyperbola, y equals 12 over x. And remember, in general, that is going to be your reciprocal graph, which is 1 over x, stretched vertically by a factor of 12. So it looks something along these lines. This is a different line. This is not a tangent line to your hyperbola. This is some other line. And what you know is that you're looking for tangent lines to this hyperbola that are parallel to this line. Well, it's a line. Let me solve it for y. This is the line y equals negative 3x. So that line has a y-intercept of 0 and a slope of negative 3. So this is going to be a really rough sketch because I don't have any scale on this, but generally this should look something along these lines. Pretend that's a line. Okay. So where on the hyperbola will I find tangent lines that are parallel to this one? Well, maybe right about here. And maybe again right about here. Give or take, those are the lines I'm looking for. I'm looking for the points on the hyperbola that have these tangent lines to them. Okay, so if these two tangent lines are going to be parallel to the red line, what do we know about the slopes of parallel lines? They have to be the same. So I need the slope of my tangent line to be the same as the slope of this red line. Well, what is the slope of this red line? It's negative 3. So listen to what I just said. I need the slope of my tangent line to be the same as the slope of this line. Slope of your tangent line is also known as the derivative, and the slope of this line is negative 3. So the strategy to answering this question is going to be taking your derivative and finding out where is it equal to negative 3. If you want to know where your derivative is equal to negative 3, set it equal to negative 3. So first let's find the derivative. Keep in mind that 12 over x, you could use quotient rule, it would not be wrong, but I'm going to choose to first rewrite as 12 times x to the negative 1. So the derivative, y prime or dy dx, is negative 12 x to the negative 1 minus 1, which is negative 2, also known as negative 12 over x squared. So where is this derivative equal to negative 3? So I take negative 12 over x squared and set it equal to negative 3. A couple different ways to do this. I'm going to cross multiply. So I'll get negative 3x squared equals negative 12, so that x squared equals 4, so that x equals plus and minus 2. Don't forget that plus and minus. That's how I'm going to pick up two different points. So I've solved for x. Does that mean I've answered the question? Not quite. We're looking for points. So these are the x values where I have tangent lines that have slopes of negative 3, meaning they're parallel to this line 3x plus y equals 0. What I now need are the points. So let me go ahead and calculate those. If x equals positive 2, where should I be plugging in x equals 2 to find my point? You should be plugging into y equals 12 over x. Then y equals 12 over 2, also known as 6. So the ordered pair, so the first ordered pair is 2, 6. And if x equals negative 2, then y equals 12 over negative 2, which is negative 6. So that's negative 2, negative 6, which even according to this rough sketch actually looks pretty good. This would be the 2, 6, and this one would be the negative 2, negative 6. So those are many of our differentiation formulas. We still have one more that we need to cover, but before we do that, we're going to see if we can discover some of the derivatives of trigonometric functions first.